All right, we're going to solve a few examples here where we're using Newton's third law. Now, in general, we're still technically analyzing the motion using Newton's second law, in that the acceleration that any object or system of objects experience is due to the net forces acting on them. Newton's third law comes into play in terms of how these two boxes, for example, in this case, are interacting. So we have our two blocks on this frictionless surface attached by a rope with negligible mass. That's so that we don't have to account for the force of gravity acting on that rope. It tells us that this rope in here will break if the tension exceeds 500 newtons. The block on the left being pulled by a force towards the left, we want the maximum magnitude of this force such that the middle rope will not break. Now, as we look at these problems, sometimes it's easy, in this case it's fairly easy, to look at this system as if it were one single box with a mass of 50 kilograms. If we do that, we know that that box has this pulling force to the left. There's a normal force and a force of gravity acting on it. We're assuming this frictionless surface, as the problem indicates. When we look at the system, though, as if it were just one big 50 kilogram mass, we do not end up seeing the tension in between the two boxes. And that's because it's internal to the system. But looking here, I'm going to call to the left positive, because I know if this force is pulling to the left, the whole system will accelerate towards the left. So when I write out net force in the x direction equals mass times acceleration in the x direction, this force, F being the pulling force, is going to equal this entire 50 kilograms times whatever acceleration this system of boxes has towards the left. So we don't have enough information to solve for a numerical answer yet, but that's okay. It's helpful to go ahead and just start writing out what we do know. Now, the other things we can look at is look at just the 30 kilogram box, or just the 20 kilogram box, or both. So for example, if we're looking at just the 30 kilogram box, we know this pulling force F is pulling to the left. We know there's the tension between the two boxes to the right. And again, the maximum tension this can have is 500 newtons. That will be the 500 newtons when the pulling force F is the biggest it can be. And that's what the problem is asking for. What's the maximum magnitude of this force? This box, of course, experiences a normal force up, force of gravity down. When there's no friction, we don't really need to write out, in this case, the forces in the y direction, but you may recognize that the normal force will equal mg. In the x direction, when we want to talk about the net force in the x direction, I'm not calling this mass m1. I'm still calling to the left positive, because that's what I chose to say in the previous step. I can now say the net force will be the pulling force to the left minus the 500 newtons to the right, that tension. So that represents the net force. So that has to equal this mass times its acceleration. So F minus 500 is equal to 30 times A. So technically we now have a system of equations. This F is the pulling force, which is the same thing in both equations. The acceleration is the same thing. In this left equation, that represented the acceleration of the whole system, but the whole system has the same acceleration as the individual boxes, so these accelerations will be the same. We can solve this right away, but I'd like to show you also, just because I can, the 20 kilogram box. So the 20 kilogram box is this right-hand box. The only force it is experiencing in the x direction is the tension to the left. Y direction, it of course has the normal force and the force of gravity. But I don't write the force F, this pulling force, on the 20 kilogram box because it is not directly acting on this box. So when we look at the net force in the x direction on this box, I'm going to call this M2, all we have is the tension to the left. So I'm being consistent in terms of to the left being positive. And again, I've chose that just because I knew that was the direction they would move in. So both that pulling force and the acceleration will end up being positive. On the case of the 20 kilogram box, the tension is to the left, which is creating the acceleration. We know the maximum tension is 500, which is we're assuming the maximum tension to find the maximum pulling force. The mass is 20 kilograms. So this particular box, we can solve for the acceleration right off the bat. The acceleration of these boxes would be 25 meters per second squared. And the fact that I get a positive answer, which we expect, is the acceleration is to the left, just like the force. This acceleration can go in for A in either one of these previous two equations we wrote out. I'll put it in the far left one, just since that's simpler. The maximum force, the maximum pulling force, will be 1250 newtons. Now that doesn't mean that's how hard we need to pull. We can pull to the left at any force. But if we pull with this 1250 newtons, that's the biggest it can be and not break that rope in between the two boxes. If we plugged in the 25 in the middle equation, we would come up with the same answer. So when we have two objects moving together somehow, typically we end up with a system of equations. We can always write the equations that describe the net force on any one individual object. Those together become the equation we wrote for the system as a whole. So we only needed two of these to solve the problem.